I mean, it's a good strategy, yes. Looks like of the multiple choice, 4 was a hard one. What was 4?
Or use KB.
Ah, KB. If you got KB, how do you get a KA? -14, beautiful. Also, you can just write it as a base hydrolysis problem, which is probably the way to go on this one. If you do B plus H2O will give you B with an H plus taken onto it plus OH minus. And then you can calculate the OH minus concentration and the POH and then subtract 14, or do the inverse instead of the -14 to get the H plus concentration correctly. Let's see. It's like 3 and 5. Yeah. Oh. Say again? There never is. No? You think it's somebody else's class. Because I just type these directly into my Excel sheet, type your answers in there, and that's how it codes for the percentages on those. And then I type in what fraction of the hard coded, the missing ones here that you got correct. And then I put it right straight off the Excel sheet. So, but it should be in Georgia. They did show up in Georgia, yes? Okay.
You know where,
Yeah. Oh, on number 8. So, the equivalence point is the vertical where the pH changes drastically. Okay, that's how you can tell you're at an equivalence point. So when you get the vertical part of it, that's your equivalence point. Skipping B for a second. The reason that that's an equivalence point is you've run out of buffer at that point, right? Making it, therefore, also a poorly buffered region, right? By definition, an equivalence point for an acid-base titration is your poorly buffered region, right? There are 2 of them on this curve. There are 2 equivalence points on this curve, and you could have picked either of them, and either was correct. Then a well-buffered region is the opposite. That is the flat area, right? Where you still have a lot of both acid and base. You could even say that you have half of your total species as acid species and half as the conjugate base species, making that the half equivalence point. However, Murph helped me look for any mention of half equivalence points anywhere in the lectures or the text. I really was sure it was in the textbook, but I think they changed it out from under us. And we could not find it. So I went back and zeroed out that that question points-wise. And after I zeroed it out, recalculated your grades, and if your grade went up, I gave you the higher. If your grade went down, I left it where it was. So if you saw your grade change as I was putting them in, that was fine. Well, actually, it's back because it's after yours was in. All right, other questions? All right, cool. All right, so now Unit 4. We have 2 principal concepts in Unit 4. We have thermodynamics. It's going to be this lecture and the next one. thermodynamics, and then we have redox, okay? And so the electron balancing, stuff like that is going to be the last bit that we get to. So, into thermodynamics now, I'm going to start with hopefully a review from Chem 1. Y'all remember this enthalpy idea, the delta H? What do you remember about delta H? Well, okay, hold on. Let's talk about what y'all are saying. A little bit louder.
Well, Miriam said it changes temperature. It's changing.
Okay, the H is probably stands for has, not heat, but okay. It's enthalpy, right? It is, what do you mean by heat, Mark? Yes, it is energy. Keep going. Is it kinetic energy? Let's talk about that. What do you mean by heat? What is kinetic energy that you're mentioning? Let's go to physics here. Moving stuff. All right, cool. So the energy of moving stuff. What stuff are you thinking of moving? Particles in a system. So, what would this look? All right, we'll come back to the moving particles. I'm not sure about that. It's going to get complicated because there's another piece today that we're going to talk about that has to do with moving particles also. Okay. What were you talking about temperature, Miriam? What were you talking about temperature?
Like some changes.
So that's where you're seeing it on the pragmatic side, right? Like we can't. There's no machine called a delta H measurer. There's not such a thing, right? All we can do is measure changes in temperature for a reaction, right? And then calculate these things. Nobody has ever seen a delta H. And in fact, it doesn't exist. It's a concept. It's a bookkeeping concept, right? So there are joules of energy, but where they are is a bit problematic. So the way we tend to do this here at Dolphin is we divide this up into a little bitty bites in Gen Chem 1 to disagree with because you have no concept for what it means and it doesn't lead to the larger concept without what we're going to do this week, okay? But it's a little bitty concept in Chem 1 and then we're going to hit it harder now, okay? So this delta H, let's look at what I've got up there. Delta H equals delta U plus P delta V. What is that? Strange random coding. I am not going to take an empty derivative. So, but you will later in PQ. So, okay, keep going. What is it? What was this? What was that stuff that we did? Remember that?
Like Tesla's law and.
Hess's law, okay, this one's not Hess, but yes. Keep going. It had to do with delta H's, but. Yeah, okay, now be careful with that. That gets people, right? Because we started out the thermo idea with Q, that's heat, equals MC delta T, right? But that C assumes that you know the chemical and, very importantly, that the chemical doesn't change. Okay? Here we're talking about a reaction, so the chemical is changing. You couldn't use a C here because you got one chemical on the reactant side and a different chemical on the product side because we have a chemical reaction. Okay? What's this? Anybody remember the delta U thing? Did y'all have Dr. Shannon? Did he talk about a delta U? No? Okay, did you see it in AP? No? Okay. It is a potential energy. Why are you thinking that, Brady? Yeah, okay, in physics they use U for potential a lot of times. This is a different kind of potential energy. This is chemical potential energy as contained in your bonds. Okay? So your delta H, in fact, we're going to think of, and this is an oversimplification, it's not true, but it's going to work for our purposes here. We're going to think of the delta H as the difference in energy contained in the bonds of the products versus in the bonds of the reactants. Okay? So you have a total energy in the bonds that make up a, let's see, let me think of a good example here. So, there are bonds, there are covalent bonds, pure covalent bonds, holding the hydrogen molecules together, right? Well, each of those bonds has an amount of energy associated with that bond. There are pure covalent bonds holding those diatomic oxygens together also, the O2 molecules. There's an amount of energy associated with each of those bonds. Then we look on the product side, H2O, and there's an amount of energy associated with each of those oxygen to hydrogen bonds. You know, they're polar in this case, they're still covalent, and there's an amount of energy associated with it. So how we tell about this reaction then is we'll take and we'll add up all the bond energy on the product side, the H2Os in this case, and we'll subtract all the bond energies on the reactant side, the H2s and the O2s in this case. And so products, sum of the products minus sum of the reactants gives you the delta H of the reaction. Does that trigger any memories from what you did in Chem1? Did y'all do products minus reactants for delta H's? Maybe a little nod here. Mercy's not sure. You do remember something about that? Because it's going to come back. And thankfully, good God, let's be thankful for what times it does happen. We're going to be consistent. We're going to do it the same order this time. So the new stuff, we're also going to do products minus reactants. No curveballs there, okay? That's going to be good. All right? Stop here before we go further. Okay, we don't know how much energy there is in a bond. We don't know this. You can't get in there and measure it, right? You can't get in there with a little tape measure. All right, now we can sort of measure the distance between the two bits using lasers and other lightweight capture and stuff like that. Again, there's a lot of assumptions that go into that. And so we're calculating this energy, and then if you calculate it from basis sets, it never adds up to this, so we don't really know what's going on. Well, so we use this delta idea because we don't have to care what the absolute energy associated with it is. All we care is relatively what are the energy in the bonds of the reactants versus products, because we're going to do products minus reactants. So if we measure them all relative to the same thing, we set up a system, then all should be good, right? So we set up a standard state. Do y'all remember the standard state for delta H? What has a 0 delta H? We'll come back, maybe. Okay, we'll come back to this because we're going to set up our standard state again. All right, over here, this is pressure times delta V. Who's had to put air in a car tire? Anybody? Okay, so Lori, you're putting air in your car tire is sitting there, it's gone flat. You put air in it, what happens? Putting air in, and then what? What happens to your car? As you're putting air into that tire, right, that's sitting flat on the ground, putting air into it, what happens? Lifts up, right? So you have used air pressure, and you change the volume of the tire, right? And you lifted the car with it. That's work. That's by definition. That is moving a mass through a gravitational potential. That is the definition of work. Okay? So in chemistry, we tend to define our work in 4 different ways, but this is the easiest one. As pressure times the change in volume. Okay? And so y'all need to know, Murph, that does depend on which one you're doing, which version of work, whether pressure can change, whether volume can change, whether other things can change, and those all will have different codings on them. And right in there, actually, when you're doing this, the deltas are in partial. It's on which dimension. Okay. So you do a partial derivative, so you do an integral based on the partial derivative volume, a different integral based on the partial derivative pressure, and you make a surface out of it. So I mean, it's really cool stuff. Okay, but that's our work term. So when I refer to the work term, this is where it's coming from. So we can substitute in, and so now we have delta H is delta U plus the negative W, the negative of work. Well, we also had, now this is, when I say we have earlier, this is because this is one of my Gen Chem 1 slides. So if this is cryptic, make sure you go back and look at the Gen Chem 1, the review materials that I have up on this stuff, because this is all Gen Chem 1 stuff, right? Now your delta U, here's where your heat is. See that? It is heat plus work. Now this is heat evolved that Miriam said you can see changing the temperature of a solution, right? That's that heat right there, that Q. And it does relate to your Q equals MC delta T. That delta T, what Miriam can measure. Okay. So all this is just calculating backwards in the dark from one little thing that we can see, which is a change in temperature, right? This is our Q, our actual heat flow. So I'm going to substitute in. What am I going to substitute in here? Think in algebra terms. What am I substituting here? I might need to do a integration by parts later, so let's make sure we get the substitution. So I'm putting this in that I defined here for this. I'm putting it in for this delta U. Well, what's that going to do when I do that? Ah, you're right. Leaving the delta H is just the heat, the joules of heat energy evolved from a change in those bonds from the product side minus reactants. Okay? Okay. Now remember exothermic and endothermic reactions. What do you remember? So anybody was going to help? Go ahead and help me.
You say it's the opposite of what you think it would be.
Okay, let's think about it. Because I worry here that a lot of times it seems opposite because people try to just memorize them. Right? So instead, let's think of it this way. If I take the total delta H of my products, right? What order are we going to do? Products minus reactants, right? So if I take my total heat, make up a number. How many joules of energy in my products? Make up a random number. 2,000. Okay. 2,000. Now, if I subtract all of the bond energies in my reactants, right? Now the reaction I've written up here is burning hydrogen in oxygen. Do you think that is likely to be exothermic or endothermic? Be brave, be brave. Hydrogen set on fire. Is that going to be exothermic or endothermic? Very, very exothermic, yes. Right? Very exothermic. You're setting hydrogen on fire, right? Okay, so does that make sense then? If this is an exothermic process, it releases energy, right? That's what we're saying, exothermic, it releases energy. Well then, if I'm doing products minus reactants, right? Which one had more energy? If this side over here is releasing energy as it happens, then which side are we going to say had more energy, the products or the reactants? Reactants did. So the reactants have more total energy in them. So when you do product minus reactants, you get a negative number. You just said that the reactants should have more energy in them, right? That's why we define products minus reactants, delta H negative, to be exothermic. There's deeper than just trying to memorize that exothermic is negative. Okay? Okay, and I pointed out, again, this is one of my Gen Chem 1 slides. I pointed out that you need to look these up in the back of your book. You have this whole appendix, what is it in this one? G, appendix G, and you go look up your delta H's, right? And so in this case over here, we look up the delta H for water, H2O, right? And then we could look up the delta H for hydrogen, but we would actually find it to be 0. And we would look up the delta H for oxygen, we would find it to be 0 too. But products minus reactants, and we would get that delta H for that reaction. Okay? Does that make sense? Remember that? Products minus reactants. Okay. I pointed out in my slides up there, see the blue arrow that they need that column, and the red arrow saying that you'll need that later. Now it's later. Now it's when we're going to need those other two columns. Okay, so delta G, sorry. Oh, that's one appendix G. Okay, that's cool. All right. So you're going to need appendix G all through these two lectures. Okay. All right. So make sure you can find that. Okay. Let's talk about this idea. If you use the, Kira, if you use the term spontaneous, are you spontaneous? Yes or no? No. All right. One of your friends spontaneous? Can you think of somebody? You cannot think of, you don't have any friends that are spontaneous? You need to be friends. Yeah. All right. Mercy, do you have any friends that are spontaneous? You are the spontaneous one. What do you mean by that?
Just up and do everything.
Ah, you'll just up and do a thing, right? That's spontaneous. Does that make any sense? Okay. We're going to use that terminology as it relates to chemical reactions. So remember I brought back here the hydrogen, right? And we lit off the hydrogen, right? And so we burned a little bit of its hydrogen, right? Well, then there's more hydrogen coming out. Am I going to have to light it off again? Oh, okay. Well, that came, and the more comes out of that, am I going to have to light it off again? No? Why not? Why not? All right, let me use a different example. Let's see. Who's into cars? Anybody into cars? All right, Owen, what you got?
I don't have. I just.
Just slide. Okay, so let's say, Owen, that, so my buddy did not go caving with us, right? Remember, a week ago Saturday, because his cousin found what is it, 66, was it? I remember what year it was. A 66 Mustang running for $4,000. Like, yeah, I guess you gotta go get that. Yeah. So he was gonna get, oh, okay, now let's think about it. Let's say you ended up with 66 Mustang, right? Now, is it probably gonna be growing rust? Probably. Y'all see that? Well, Owen, what are you doing to cause it to rust? Well, what are you doing to it to cause it to rust?
Well, it's not that brain, it's actually.
Yeah, but did you go initiate a rust reaction?
No.
Not on purpose. Are you saying you did? That is a spontaneous reaction. Okay? A reaction that just happens. Now, you gotta actually work to get that 66 Mustang to not rust. I promise you're gonna work hard on that, right? I was in the Navy, I was on a ship built before, but commissioned in 1963. Worse, it's Navy, so it's been sitting in salt water the whole time. We had to work like hell to try to keep that thing from rusting. right? Okay, so the rust just happens. It's spontaneous. That's what spontaneous means. Well, let's see if we can figure out how to use that. Oh, I had another last semester in Chem 2. I had a guy back in Afghanistan, so I was using some examples. Anybody know white phosphorus? What is it? Yeah? How do you? What is your context for it? The game, maybe?
Or just like I know.
I was just wondering if there's any of the, like Fortnite or any of the games it is.
I think it's in Call of Duty.
Call of Duty, all right, tell me about it. Tell everybody about it.
It's like a kill streak. You can get a certain amount of kills. The plane runs over, drops this white stuff.
Okay, wait a minute. So this plane is dropping this white powder, right? Okay.
And when it touches the bad guy, it burns.
It's not just bad guys.
It burns your bones, doesn't it?
It burns everything.
Yeah.
White phosphorus is a real thing, right? And it burns, it just does. If there's oxygen around, this happens, right? And this arrow right here is called fire. Okay, so this happening is lots of fire. Does that make sense? That's a real weapon. It's usually not dropped as powder. It's actually usually dropped as containers that burst open once they hit it. But that's slightly different. It'll burn through a tank. So, yeah, that's what we're doing. All right, so you'll get the idea of spontaneous, right? Okay, cool. All right, and here's our hydrogen. Now that hydrogen that I was claiming, now this is a little complicated here because just the hydrogen coming out, it's like, it's okay-ish. God, please don't have a spark, right? Because once you have the slightest little spark, then all the hydrogen's gonna burn, right? Or all the oxygen, depending on which one is your limiting reactant, of course. But there can be a need for what we call an activation energy. We'll talk about that. But once it gets started, all of it burns, right? Once you get over that initiation energy, the activation energy, then it is extremely exothermic and it is extremely spontaneous. Okay? That making sense so far? Good, because it's about complicated. You ready? All right, spontaneous reactions. I want you to choose which of these, and I want you to talk to each other about this. Just start yelling out stuff. Start talking about it out loud. I want y'all to choose which of these four reactions you predict to be spontaneous and why. Go.
I don't know what that's all.
Oh, and for this next exercise, you are part of the front row. Okay? Each row, now discuss amongst yourselves and come up with an answer that your row is going to give. How many of these you're going to claim are exothermic? If you're ready to defend your answer. Let's go talk with your group. I'm going to specify, by the way, that these are going to be at standard conditions. Okay, in case that comes up. At standard conditions, 1 atmosphere of pressure, 25 C. What else do we need? 1 molar concentration to air. Rows have your numbers? Lock it in. All right, Owen, what's y'all's number?
I'm thinking one.
So two of them are, 1 and 4, okay? Kira, how many are exothermic? You think first and second one, but you also think two of them. All right, Irv?
I agree. First two.
The first two, which you say two of them, all right? Which two?
The top two.
First two. All right, ladies? How many? Which two? All right, so all but Owen's group said the first two. Owen, you said which two?
We're talking about spontaneity.
I agree. Talking about spontaneous, keep going. Hang on, you may have some reasoning here, because you said which one? 1 and 4. Now, why do you think 4 is likely to be spontaneous? What's your reasoning here?
We said that was last. Yeah.
I agree with that, it would be.
In that case, then the 4 could be a spontaneous. Imagine this.
Interesting. Okay, Kara, you ready? Ready? Now, what were our conditions?
So 1 molar, like.
1 molar concentration, and 25 C, and 1 atmosphere pressure. Okay? All right, no one chose number 3. Let's look at number 3 specifically, Kira. What's on the left? Well, solid water. What do we usually call that? What's on the right? Okay, now, no one said that if I come back here and I hand Kira some solid water, that it will spontaneously, at these conditions, become liquid water. Would you like to revise your thinking? Do you think it will spontaneously go from solid to liquid, sitting on your desk? I do too. Okay, revise. I did ask you. Oh, okay, well, the first two are exothermic. Which ones are, I thought I said which ones are spontaneous. Sorry. Okay, I meant to ask which ones are spontaneous. Yes, the first two are indeed exothermic, you are right. But now revise to how many are spontaneous. Let me ask, yeah, check with your group, check with Owen, y'all. Check with your group, we'll do it again. How many are spontaneous? Obviously, I've given away number 3, okay?
The first one is correct. I agree. Second, also what happened pointing out.
Mercy, how many? Guys, how many? 3 of them, the top 3.
Which one are we saying?
How many are spontaneous?
I would say
3 of them, which one's not?
the first.
First one's not? Okay.
Yeah.
Okay. You're on second. Okay.
Discuss the group work.
That, I mean, y'all. All right. My claim is that even though those two are indeed exothermic and those two are endothermic, all 4 of these are in fact spontaneous reactions. So the first two the first one is methane burning in oxygen, just like our hydrogen. That's exothermic. I heard Braden talk about the acid base. Y'all just did this. It's acid and base are, well, yes, you know that just happens, right? Okay, so that one is spontaneous, all right? Then this is Kira's block of ice, right? Okay, and this one is ammonium nitrate. It's a chemical. It looks crystalline. It's not always, but it looks like it is. And if you put water in it, it dissolves quickly, right? Okay, so that one also is spontaneous. Huh. So, all right, but wait, so we can't guarantee that a spontaneous reaction needs to be exothermic, apparently, right? It would make sense, the world would make sense if exothermic reactions were spontaneous and endothermic ones were not. That's not the way it works. There must be something else going on. What else could this be? What really, really important concept in the universe is there? Getting close, getting warm there. What else? Anybody like to read Isaac Asimov? Somebody reads Asimov. I know you should know it, because Asimov definitely says this is the thing that ends us. This is the heat. They call it heat death of the universe. Have you heard that term? What's that about?
Isn't it like because the universe thing? I don't know the exact reason why, but it's something like there's a theory that eventually the universe will collapse back in on itself.
Well, that's a whole different.
That's the
problem, yeah.
I don't know. All I know is it's bad and we're probably not going to see it.
So we're going to claim that you can have a spontaneous reaction or a non-spontaneous reaction. You can run it in reverse. But what tells us whether it's spontaneous or not? Let's look at another piece. Keep thinking on that. Keep thinking. We're still trying to figure out what that other thing could be. What is that thing that drives whether or not something happens if it's not whether or not it's exothermic? That's apparently not it. So we need a deeper concept than just the bond energy relationship, the delta H. Let's look at this problem. So color-coded hot piece of metal and a cold piece of metal. Block X is supposed to represent something with a higher temperature than block Y. Okay? Now, thought experiment. You've got block X is higher temperature than block Y. You bring them together, touch them together. What's going to happen in this thought experiment? Ooh, how do you get it to?
Because,
How do you get it to move?
because that's,
You just talk to it and get it to.
it goes from a high concentration to a low concentration.
It's spontaneous. It spontaneously does this, right? It's spontaneous the way heat will don't. So will it ever stop flowing? Will heat stop flowing from block X to block Y? Won't when?
When the temperature of both blocks.
The temperature becomes the same, right? Then it will settle down. That makes sense. Okay. Now this is a little hidden thing down here, but it's extremely important. Total amount of energy in the system, block X plus block Y, does not change. That makes sense? However many joules of energy you got. At the beginning, you still got the same number of joules of energy at the end. You just might have put them in different buckets or in different blocks in this case. Okay? So this some other factor that we're looking for is called entropy. How many of you have heard the term anywhere? I'm going to ask where. So, where have you heard the term?
Chemistry class.
Okay.
Yeah, the high
Where,
school, yeah.
okay. Where is he? Where have you heard the term? When I talk about entropy, come on. Okay. All right. Anybody heard the term outside of chemistry?
There's a song,
Oh.
but I think it's actually about how, and it,
The entropy of My Little Pony, we should totally grab it.
no, it's, I think it's My Little Pony fan song, but it's just a pretty good song. And it's,
What's the bit about entropy?
I don't really know My Little Pony, but it's about,
Okay.
okay, so there's a villain called Discord or whatever. And then, I don't know all about it, but it's something in entropy.
I bet it relates, actually. I bet. I need to look that up because I bet it does relate to this because he's talking about Discord. Yeah, okay, all right. You know this song? Can you fill in the gaps?
It's been years.
It's been years, okay. All right. Any other context about entropy? Huh? Or what?
Something a few years ago, someone misconceptions of the universe.
Oh my God, there's so many misconceptions about entropy. Do you know,
Change.
do you know when you learn and fix all of your misconceptions about entropy? You know where you learn that? I don't know. I don't know that. I have plenty of misconceptions remaining about entropy. I promise you will not leave this class with all of your entropy misconceptions cleared up. I'll do maybe a little, but not all of them, probably. Okay, there are lots and lots of misconceptions about entropy. Well, let's try to figure out what it is. Okay. They told me before when I start doing this, it feels like I'm like, wait. Did we just work to another class? Just go with me for a second. Okay. Do y'all remember? Now I taught it ninth grade algebra, but do y'all remember probability, basics of probability stuff? Do you remember that? Like what's the chance of rolling a 1 on a, or let's say rolling a 6 on a 6-sided die? What's the chance? What's the chance of rolling an 18 in 3d6? Well, let's get it easier. What's the chance of rolling a 12 with 2d6? How'd you get that? How many possible answers are there then? There's more than 12 different things you can roll. 1 in 36. Yeah. Okay, because so then what would you guess is the chance of rolling an 18 in 3d6? 1 in 6 cubed, whatever that is. Yeah, I don't know the number, but it's small. 3 something. Anyway, okay, so channel that stuff from probably early high school, I guess. But okay, so let's think about it. Okay, what I have up here is I've constructed a thought experiment here. I've got these 2 glass spheres attached together, and that's supposed to be a valve in the middle that I can open and close. That make sense? Okay, so we're going to take this that's a blue part in one of my spheres. Okay, got it? Got a single blue particle. It's in the sphere on the left. Okay, I am going to open the valve in between. We are going to go away for the summer. Come back after the summer and check where are we going to find the blue particle. Where are we likely to find the blue particle? Why?
We have no idea.
Okay, it's true, we have no idea until we look, and we are going to go there. But, well, if something would cause it, let's say maybe there's too much stuff on the left, and so it moves to the right. Oh, wait, now there's too much stuff on the right, but it moves back. Right? So, now what are you saying, right?
Saying we have no idea until we look.
Okay, so what are our odds then?
I guess 50-50.
I'm going to claim that they're 50. I'm going to claim blue particle could be in the left box, or blue particle could be in the right box. Does that make sense? Yes? Okay, good so far. I'm going to claim there is a 1 in 2 chance, 50%, left box. Also, there is a 1 in 2 chance, right box. Yes? My thought experience? Yes. Yeah, I mean, technically, but I think for the thought experiment, let's claim that there's like 0 volume in the middle, just to keep it simple. Does that make any sense? But yeah. Okay, so keeping it simple with just 2 places that the particle could be, it's got a 50% chance of being in either. That makes sense conceptually. So far? Uh-oh, got more complicated. Okay, same thought experiment. We got a red particle and a blue particle, right? Go away for the sun, open the valve, go away for the sun. It sucks to go away and not remember to open the valve, wouldn't it? Okay, all right. But you open it, you go away, and you come back. What are you going to find? What do you think is going to happen? You're gonna-
Same thing as the last.
So it's gonna be 50% to find them on the left and 50% to find them on the right.
Not at the same time.
Oh, wait, Lori, what do you think? What am I gonna find this time? A little more complicated. Yeah. 1 and 4 that way.
It's in the same.
So they're in the same one? Ooh, I think I'm gonna question that one. Let's see. Guys, what do you think? Morning. But where we are to find the particles. Okay, tell me some of them, please.
So like, they could both be in that one,
Good, she's on the right track. Keep going.
or they could both be in the other one,
Or,
like the blue one on the left, and red on the right.
oh, okay, let's look at that. Ah, you're on the right track. So this is one of your options, right? That was one of your options?
Yeah.
Like that. All
Right.
right, y'all see what we're doing here? Right? So we're sorting these guys out, all the potential places that our particles could be, right? Okay, but remember that we were talking about subatomic particles, usually maybe electrons, right? Okay, so that's going to come up. Let's see. Because I actually can't tell which electrons are red and which ones are blue, right? That makes sense? So if I gray them out, right, then this option looks the same as this option if they're just gray electrons. Does that make sense so far? Yes? Now, what about the probabilities? Say it again? I disagree. Because the red and the blue electron actually are separate. We just can't tell them apart. So there are 4. So our denominator here has to be 4.
So would it be, let's see.
Exactly. Say that loud, please.
There's a 25% chance that both will have one the other way, and then there's a 50% chance once of the other.
And last one,
There's a 25% chance there's one.
but a 2 and 4, 50% chance of this middle part, if we cannot tell the particles apart. Does that make sense? Good so far? Ready for the next step? You know where I'm going next year? What would you do? Yeah, another part. Uh-oh. Now what? What you gonna do now?
50, they're only do one,
That's an option.
so you're gonna move to the other side. 2 will stay, 2 will go over. 2 other ones.
And you can use the colors, and that's why I put the colors in here to help you conceptualize what all the options are. So do it with colors and then gray them out after. Does that make any sense?
So I think all 3 one side, 3 on the other.
That's 2 things.
And then blue on one, red and green on the other. And then green and green on one side, blue on the other, red on one, blue and green. I'm losing how, but it is.
Yeah, it's hard to visualize, right? And so it might be that you would want to make a structure and actually draw it out, right? Okay, let's see. Like that? Yes? Like this. Those are my options, guys. Does that make sense? Let's give me percentages then. Remember to gray them out. Oh, also I can't tell my boxes apart. Because while we were gone for the summer, Murph came in and he put the device on a little roundy turntable and spun it. Now we can't tell that apart either. Does that help with the percentages? Yeah, makes it easier, right? Once we start to close our eyes to certain things, well, what's the chance of this? How many options were this? Out of 8. Now, last time we had out of what? This time it's out of 8. See a pattern? What pattern do you see? First one, by the way, was 2 options. Second one was 4 options, and the third one was 8 options. What do you see as a pattern? It is what more precisely? 2, yes. Or what's coming, I'm going to give you this on a slide in a minute. Number of boxes raised to the number of particles. Okay? Does that make sense? However, since Merck put our boxes on a turntable, right, we can't tell the middle 2 rows apart. So even though it's 3/8 that we'll get 2 particles in the left box and 1 particle in the right box, we can no longer tell until we get 6/8 or 75% chance that we get 2 particles in a box and 1 particle in a box. Here.
Get the boxes.
Yeah, you could. Yeah, so you're saying a 25% chance and a 75% chance. I agree with you. I agree. Make sense so far? Where I'm going to go with this is if we have a whole lot of particles, right? Now we're not dealing with 1, 2, and 3 particles. We're dealing with a number that's got 24 zeros on it, right? Without calculating, and Kelsey just made a face that told me that she does not want to calculate that, right? Without calculating it, where are they likely to end up? Are they likely to all end up wadded up on one side of the device? No. They're likely to be all spread out. This is why the energies, the joules of energy in those 2 hot blocks, this is why they ended up distributing to both blocks, because they are most likely to spread out both ways. Does that make sense? It's actually a very fundamental thing of our universe. This is the idea of entropy. And it is looking at your degrees of freedom and spreading out so that you basically, I'm going to call our universe a disease, but spreading out to infect all the possible boxes. Here is that idea that we just discovered, right? That it is number of boxes raised to the number of particles gives us, it's the denominator that we've been using on those previous slides. It gives us the denominator. Now I'm giving the denominator a name, and I'm calling it the microstates possible. So the number of microstates is the number of places that something could be raised to the number of particles we are dealing with, right? So, Allison, when you were in Chem, right, do you remember doing a problem in Chem of having 3 electrons in a box? Oh, okay, I thought you had. Well, you won't do a problem with 3 electrons in a box because it's too damn common. The problem that you'll see over and over again is the electron in the box, right? Because you guys know where we've solved the Schrodinger equation for now, right? You know, the Schrodinger equation proposed in, I think it was 23, I'm not sure, 20 something, right? And 1923, so a little over 100 years ago now, right? You know what the most complicated atom we have solved that equation for is? I used to say hydrogen with 1 electron. That's technically not true. it looks like now, if we ignore complexities in the nucleus, we can solve it for helium and lithium that also have only one electron, which are not real systems, right? But the point being that we can solve it for one electron because there's one particle. Okay? And other than that, it's just too complicated for modern computers. Okay. Now so this up here, this in the top equation, entropy is defined as K, Boltzmann constant, that's not going to change on you, 1.38 times 10 to the negative 23rd joules per K, times the natural log of the number of microstates. And the number of microstates, so as you divide up your system into more and more possible configurations, that is going to be important, possible configurations, it increases the total entropy. Okay? So total, do y'all remember me using it back in unit 1, me using all the middle schooler analogies, right? Yes? Okay, Kiara, you ready? Go with me on the thought experiment. Consider you were having to watch some number, how many middle schoolers do you have to watch at recess? Oh my God, 23 middle schoolers that you were having to keep up with, right? And they have basically 2 degrees of freedom. They can run all over the playground, right? Okay, think how much more horrible it would be to watch them if they could fly. Oh my God, right? Because you got 3 dimensions. Okay, that's what we're looking at, really. Nobody in the real world actually calculates the microstates. You have to underneath it, but nobody really in the real world calculates the microstates because there's too many of them. But we do think about, hey, there's going to be more freedom in this scenario than there is in that. We don't know how much more freedom there is if middle schoolers can fly. We just know it's a lot. Does that make sense? All right, here's our 2 again. 2 particles, 2 boxes, right? Or 4 particles. See how much more it stacks up if we have 4 particles? Remember, we would have to gray them out, right? So that C line, all gray, does that make sense? We can't tell those apart. These are called distributions. Microstates are how many boxes, right? So in this case would be, how many boxes would there be here?
16.
How you get 16? Yes, how you get 16?
I don't know.
Oh, it was the easier way. How many were there with 2 particles? Well, how many were there with 1 particle? How many options? How many were there with 2 particles? How many were there with 3 particles? Y'all scared me about the math. Y'all scared me. All right, let's try this again. How many with 1 particle? How many with 2 particles? How about 3 particles? Hey, how about 4?
16.
That's how we're getting 16, 2 to the 4. Okay? Yeah. All right. Which distribution is most probable to find in nature then? You go out and you look in nature, and we have a very, 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 very simple system that's got 2 boxes and 4 particles. Really, what are you going to find though? What are you probably going to find if you measure this? You talk to your group again, get your answer. Defend it. Carson, decide who you're putting on the spot.
In class.
Yeah, well, I mean, unless you got somebody else to know.
How about rhythms?
Which one's most likely?
Yeah. E or D is certain equivalent. You have no way to determine what the box is.
Anybody want to argue with Braden's interpretation? I would like for you to argue. So I don't agree with it.
They each have the same chains.
Oh, what does?
Each one of the boxes.
I don't know. Braden says, oh, I know what you're saying, Braden. You're assuming Murph's turntable again, right? That makes sense. Okay, assuming Murph's turntable, yes. But not assuming Murph's turntable, then C would be the best. Okay. Y'all starting to get deep on this. That's good. That's good. Okay? You see how it becomes really complicated? That little slight difference in the way I ask that, right? Already gets too complicated with 4 particles, and there's never just 4 particles. Yes.
If they're all grayed out, would you say that they're more likely, that it's gonna have a single particle, 3 particles over here? Because in that case, you could have B and D.
Okay, that's what I was saying. Now, if we can't tell which side is which, then yes. The turntable idea, right? If I can't tell which is the left box or which is the right box. Okay? But if we have a bond between hydrogen and oxygen, where we can tell which is the right box and which is the left box, we can start to test. We would call C the most problem. Does that make sense? I agree. Okay? All right. So conceptually, I'm trying to get to the idea that the system, the distribution that gives you the most microstates included in it is the most prominent, because that's the highest entropy. Same thing. The largest number of microstates in a distribution gives you the highest entropy, right? Because given the case is the same, larger W gives you the larger X, right? And we've also discussed that things tend to spread out into those broadest distributions they can get, right? So we have that things tend to spread out into many distributions, into a mini microstate distribution. And also that when they do that, S is increasing, right? Yes? Does that make sense? Okay, well, this is a fundamental law of the universe. I thought it was on the next slide. I'm going to call it a fundamental law of the universe in a minute. I'm going to call it the second law of thermodynamics. Okay? This is the same idea that, look, already, now I don't remember how many particles this is, 2, 4, 6, 8, 10, 12, 14, 30 particles? 30 particles, right? So 2 boxes, 30 particles. What's the chance of finding everything in the left box? Here we can tell the boxes apart. So what's the chance of finding everything in the left box? 1 in something. 1 in what? 2 to the 30. Put it in your calculator. Tell me what the percentage chance of this being is. I think we're going to see how high dollar calculator everybody has. Right? I don't know. Do you think? I don't know. I actually don't know. Does it do it? What'd you get?
1 million.
1 over that. So 1 over 2 to the 30th.
Oh, I got it.
Yeah?
Okay, now inverse.
So 9.3 times 10 to the negative 10. So that's your chance of finding this distribution. 1 times 10 to the negative 10. Already with just 30 particles, it ain't gonna happen. Right? That make sense? And 30, again, you're never gonna see a system. Well, I say never. Actually, there may be a device upstairs that can get down to, it's a very small chamber, but 600 or 700 particles. Right? So that, but already with 30 particles, we're 10 to the negative 10 chance, right? And 300 is going to be a lot more than that, right? So you see, you're pretty well guaranteed to get the spread out version. That's the idea of the second law of thermodynamics, that you're going to get the spread out version. The heat flow is going to spread out as much as possible. Well, some good news. How do we calculate delta H? Products minus reactants. We're going to end up doing products minus reactants in a minute, okay? But this is the same idea, that it's the final entropy minus the initial entropy. That's going to be defined as our delta S. All right, and things that now I told you that we look at it intuitively. We don't really, in the real world, calculate entropy. We just look at it as intuitive. So here's the order that I want you to look at it as, that a perfect crystal, okay? We'll get a little deeper into perfect crystal in a minute. But a perfect crystal could have essentially zero entropy. An imperfect crystal has a little more disorder, right? Because you're starting to be able to tell the boxes apart if it's not a perfect crystal. And then an amorphous, y'all remember what amorphous meant? In Unit 1, do y'all remember this term? Non-crystal like a glass, like a silica glass, right? An amorphous solid has more entropy than a crystalline solid. A liquid has a lot more entropy than a solid. And a gas has a lot more entropy than a liquid. Okay, that's where I got my analogy of the flying ghost torch. Right? The gas is the flying ghost, all these. Okay? Also, temperature matters. The more you heat the middle schoolers, the more you heat your particles up, right, the more entropy they will have. Here you can kind of see a graphical version of it. You take this nice crystalline solid and you melt it. Now they're free on the base of the beaker here, right, to run around. If you heat them up enough, oh, thank you. Okay.
Got that workroom?
Oh, thank you. I was going to go back. Thank you. Yes. All right. If you heat it up enough, then now they have 3 dimensions to work with, right? You have lots more entropy. So think of that, the gas represents higher entropy than the other states, okay? You can also think of a system like this, okay? If we have a solid, right? You melt it, you're increasing the entropy, you have a liquid, or if you have a solute, right? Look at that. If you mix your solute molecules, the green ones, in with all these gray solvent molecules, that also represents a drastic increase in entropy because they can move around. Good gravity. Okay, the type and number of particles. Well, we've already seen number, right? But now the type, if you can start to see blue particles versus red particles, that increases your microspace a lot. If we stop blending them together, if we stop graying them out. And then pure substances versus mixtures. All 4 of those things are drastic influences on entropy. Yep. And then this is where I was claiming that it's a fundamental law of the universe. This is heat death of the universe. I get a lot of science fiction right here. That the entropy of the universe always increases. You do a thing, whatever the thing was, you increased the entropy of the universe. So, first law of thermodynamics says that you cannot create or destroy energy. You can only transfer it around. And then the second law. The second law says that entropy always increases. The third law is what we were just doing with where we set up a perfect crystalline structure at absolute zero, and we call that zero entropy. There's also a zeroth law of thermodynamics that Brady looks like the transitive property in math to me. But basically, system A is in thermal equilibrium with system C. System B is also in thermal equilibrium with C, and A and B are in thermal equilibrium. Apparently, that is drastically important. The why is seeming all that important to me, but I believe the folks in the PChem world that it's drastically important. Okay, so the idea of the system versus the surroundings. So this is where a lot of confusion exists in physical chemistry, defining your system versus your surroundings. Okay? I think the simple layout is to think of your system as your reaction. Okay? I think where it comes up a lot of times is that I'll have a reaction occurring in an aqueous solution, and I want to call the water molecules my surroundings. Does that make sense? I think that's confusing, but it's not the reaction itself. I want to call just the reaction itself a system, and the water around it to be surroundings. All right. Let me think, see how much I got left. I better come back to these Wednesday. A homework for tonight, I believe you can do without those, but let me make sure. You can. Good. All right. Beautiful. Homework is back up and running again, so do read all of, I want to make sure of my chapter, I think it's 16. 16. Make sure you read all of chapter 16. We're going to get a little more into entropy here, but then we're going to move on to what we're going to call the delta G on Wednesday. Okay. All right, beautiful. Lab this afternoon. So we'll go up. All right, bad news. I am sorry. I'm going to apologize ahead of time. But the person that was supposed to be putting the lab together for us for this week did not get it working. So I'm going to have to cancel it. I hear that there will be some shenanigans with the sun to look at anyway. So anyway, but we do need to go upstairs and check out of your drawers. I have checkout sheets with me. We're done with Lect. So I'll meet you upstairs in just a little while. Yeah, no, we're done. Let's see if the lenses are good.